Okay, so we're very pleased to have Professor Dan Scolnic, who's going to tell us about the new excitement for measurements of the Hubble constant and dark energy. So take it away.
Great. Okay. Thanks for having me give the Zoom talk. I was really excited to come visit you all in person. At this point, I don't know if any country will allow Americans to come visit them, which is unfortunate. But hopefully, at some point, we'll solve this COVID problem on our side, and I can come visit. So today, I'm going to talk about using type 1a supernovae for measuring Hubble constant and dark energy. I know you've had two previous talks. I watched last week's talk, so I'm going to try to respond to some things from there. Maybe I'll give the impression that I've done some work that gets used a good amount, so I spend a lot of time just kind of responding to people using different things in different ways, trying to figure out what's going on. Okay, so let's get into it, and please interrupt me at any time. I want this to be a conversation. All right, so we'll start off with dark energy, and then I will go to the Hubble constant. That's kind of the plan. So often these days, kind of the Hubble constant is a bit hotter than dark energy, but I understand that dark energy also gets has been getting a lot of attention for different reasons these days. So I'm gonna kind of dive more into dark energy, then I'll get to the Hubble constant. I'll quickly give a review. I know you've now had 2 weeks on this, so I'll just blaze through this if this is okay. But I just want to give one kind of preface, which is that, and this is like the pie chart that everyone's seen before. There's dark energy, and this is kind of suddenly debatable now. And there's dark matter, and then there's atoms. And we don't know what dark matter is. We don't know what dark energy is. So considering that 95% of the universe, we don't know what that is, it would be presumptuous to think we know how this whole story is going to play out. There's likely still some surprises around the corner. We should be open to them and just follow the data wherever it leads. Okay, now how type 1a supernovae are used to measure dark energy is relatively straightforward, and I kind of go on to claim that everything beyond this is lower order effects that are less significant, and this is something I'm going to try to address. But on a top level, basically the 1A intrinsic luminosity is known to 10%, and we try to measure the apparent luminosity by correcting for the brightness for how fast it declines, and also the color of the supernovae. So on the right, this is some example light curves of different of Pan-STARRS supernovae at different redshifts in different bands, and basically I tried to measure the width of the light curves, the peak of the light curves, and the relative fluxes between the different bands to get a color. And from those three measurements, you could do some kind of standardization that is still getting a lot of new work, and you could get a distance modulus. Now, independently, you can measure a redshift, and that you could get either from the host galaxy or from the supernova. And there's been a number of papers kind of looking at Pantheon about where the redshifts come from. And I don't plan to talk too much about that, but I'm happy to answer anything that's going on that front. So then every supernova can be used kind of as a single distance modulus point on the Hubble diagram, where you get basically a distance modulus and a redshift, and from just two supernovae, you could have a constraint on cosmology. You're measuring the relative distances at different redshifts, and that could tell you cosmology. Now, to do this, so we often just make something what's called the Hubble diagram, which you see on the right. So this is kind of one of the original ones, and this is combining the high Z team and the supernova cosmology team, and the detection, the thing that shows that the universe is accelerating its expansion is basically what you can see on the bottom right, which is that type 1 supernovae appear about 25% fainter than expected. So the middle line that goes through the bottom, that is assuming there's no dark energy, and you could see that deviation of about 0.25 meg, and that's the detection of the accelerating universe. And you can also see here that there's a relatively small amount of supernovae that's being used to do this. Okay, and just for lingo, kind of when I use notation, so omega m will be relative matter, omega dark energy, dE will be dark energy density, W equation of state parameter of dark energy, lambda, and when I call lambda CDM model, I just kind of generally mean W equals -1, the cosmological constant, omega matter 0.3, omega dark energy at 0.7. Okay, now what's really interesting and exciting to see is kind of how far we've come. So on the left, this is just about the same plot that I just showed. So combining the two teams that originally detected the accelerating universe. And then on the right, this is from what I call the Pantheon sample. So this is a paper that I led that kind of is now the biggest supernova sample ever compiled and analyzed. And what's changed from the left to the right is that in the left, the base kind of 0 level is no dark energy. And then on the right, the base 0 level, the x-axis, that is omega matter 0.3, omega lambda 0.7. So you could see how good of a fit now now we're at 1,050 supernovae that you can see on the right from multiple surveys. See just how good of a fit the data is to the model. It's really incredible to kind of see how far we've come. To put this in a different way, so this is now showing the contour of omega lambda versus omega matter. So this is in the Pantheon paper. And in the black contour, that is the original contour constraining the amount of dark energy versus the amount of matter. And you can see these kind of very large contours. Then in the color contours, that is from the Pantheon sample. So you can see that in blue or purplish, that is the divine line between the accelerating universe and the decelerating universe. So you can see we're kind of well into the accelerating universe, very high significance from supernovae alone that the universe accelerating, that there is dark energy. And what you can see from this plot is that progress has been kind of relatively straightforward. The contours have just kind of converged to the middle of where there's predicted 20 years ago. Now, not everything in science goes like this, but sometimes it does. Sometimes there's a measurement made and it just kind of keeps getting better. And that's kind of the net trajectory of the field. Kind of for all these things that you hear about different ways supernovae may be broken, kind of it's been holding up remarkably well. Okay, now the Pantheon sample places the tightest constraint on dark energy to date. That statement actually was, I think, kind of true until yesterday when this huge new splash of EBOS papers came out. So various BAO, void measurements, I'll talk a little bit about where. So I think now, well, they use Pantheon, so I mean, maybe they'll say that they have the tightest constraint on dark energy. But anyway, so this is kind of almost as precise as it gets, and we get W equals minus 1.026 plus or minus 0.041. So the current data support a cosmological constant. It's consistent with the W equals -1. So kind of, as people know, the problem is that the theoretical predictions we have for vacuum energy are 100 orders of magnitude off of what we see. This is just a long-standing problem now of the field. There's plenty of other models, contrascence, some kind of modified gravity, but I think the feeling is that the closer W gets to -1, the less good it looks. You know, why should we be this close to W equals -1? And then the question that always comes up is, okay, well, when do we stop? We're now good to W equals -1 on the third sig fig or so. Do we wait for another sig fig or something like that? So the answer that I typically give is this plot that you see on the left here, which is showing the first derivative, so W sub A versus W naught. And basically this is showing either Pantheon with CMB or Pantheon with CMB and BAO and H naught. And pretty much you could see here that in the derivative space, there's just very little constraint. So we're only kind of doing that first order measurement of W. And while there's nothing, to me, there's nothing to say like, here's when we stop. What I feel is that as long as there's a clear path to considerable progress in a short amount of time, we should keep going. And I think with the surveys that are coming online, there's a very clear, very doable path to improving this significantly. So the stopping is more a matter of kind of what your ability is versus is there some fundamental limit, which I don't think we have. Okay, now I'll say generally that supernova, the latest supernova cosmology results are in very good agreement with Pantheon. So this is another project that I worked on. This is from a paper led by Dylan Brout. So this is from the dark energy survey, where they combined new dark energy survey data that was not in Pantheon with low Z supernova that was in Pantheon. So there is some overlap with Pantheon. And we do for this big blinding process where we make sure not to look at anything, so we're not trying to force anything. And we got W nearly identical to -1 with kind of a bit bigger uncertainties than Pantheon, just because there were less supernovae, since we just tried using DS.
Dan, when you compiled the Pantheon data set, can you comment on the blinding process there? Because I think I almost feel that everybody's biased by Lambda CDM.
Right. So yeah, so for Pantheon, I blinded. My issue is that what's tough for supernovae, or I think for me personally, is if I'm already using data where someone, possibly myself, has gotten cosmology from, I feel like I can trace a little bit in my head how different systematics are shifting things. So I don't, for Pantheon, I don't want to like boast too much about blinding, because a lot of the data was used in JLA or my old pan-stars analysis. So I felt like when it's iterative, blinding becomes a little bit less boastworthy. Whereas like for DES, that was a totally new sample. We analyzed it from scratch. We understood it much less than kind of things that were in Pantheon. So I generally am nervous when people use blinding as just like, trust me because I blinded. I think it should be trust me because you can reproduce it. But I just want to try to be as honest about this as I can. Does that answer your question?
Yep, that answers it. Thanks.
Yeah. Okay. All right. Now, well, I want to kind of make maybe the most critical point in this talk, which is my career is based on type 1a supernovae. That's what I do the measurements, my measurements from. But you could totally remove supernovae, and you still have very strong evidence of dark energy. So this is a great plot from a recent paper from Sesh Nandathar, and he basically compiles all the different probes that show that the universe is accelerating, a non-zero lambda. So you have Pantheon that's there in blue, but then there's BAO, there's voids, which has really kind of matured just in the last year as a new measurement. And then Planck itself, when you're combining all its temperature, polarization measurements, it also significantly prefers a non-zero omega lambda. And actually from this EBOS paper that came out last night, there's a really nice thing where it said, BAO measurements alone lead to omega lambda 0.637 plus 0.08 or so, an 8 sigma confidence detection of a cosmological constant without any information from the CMB or supernova data. So this is kind of now a joint picture. You can't just try taking down supernovae and say, all right, well, there is no dark energy. There's too many other probes at this point. And kind of there's also a number of external evidence that supports omega matter around 0.3 or these different kind of pieces, but maybe not as direct for dark energy. But it's not just supernovae. There's now multiple probes. And if you take supernova down, the whole dark energy framework doesn't go down with it. So I'm going to try to defend supernovae, but I kind of want to give this context that it's not just supernovae. Okay. All right. So let's dive into kind of what's happening. So what I found kind of having Pantheon out is there's kind of 3 main outcomes that have been seen when someone finds something that can be approved with type 1a supernovae. So the first is they say, okay, well, I have redone this piece of the analysis, and this is a systematic. And so in my Pantheon analysis, I think I had like 74 systematics. And so this will be a 75th systematic if it's something that we didn't look at. So that is, I think, is totally great. But what I find are the much more popular options are someone says, okay, I found something that can be improved with type A supernovae, or that might be different than what people have done. Therefore, there is no cosmic acceleration, or therefore there is no more Hubble constant tension. And it is a bit of a kind of strange culture that seems a bit unique to type 1a supernovae, where option 2 and option 3 are reached so quickly. Now, I think the reason that this is happening with type 1a supernovae is partly just accessibility. I think, you know, for type 1a supernovae, we release redshifts and distance modulus uncertainties and a covariance matrix, and from that you could do anything that you want. Whereas, you know, if it's something like BAO, or if it's Planck CMB measurements, to kind of to get into it, it's just much harder. But so here I'm showing kind of two popular claims that I'll talk a little bit about now. So one is from Subir Sarkar, which is saying that the new study says cosmic acceleration, dark energy don't exist, or one that you heard about last week, which from Kang et al., which says new evidence shows that the key assumption made the discovery of dark energy is an error. So this is kind of a thing that keeps happening, and overall, kind of what I say to it is that this is often kind of taking one piece of the analysis, and there's very little validation of kind of, you have your own method, have you checked that this can return what you think it's going to return. Whereas kind of when I put out Pantheon, I released thousands of simulated light curves and said, okay, before you try out something, here's the truth, here's realistic looking light curves, see that you could recover what I put in, and that's all fake. And then, you know, you could trust that you're doing the right thing. As far as I know, no one has used those simulated light curves, but they are out there on my GitHub page. Okay, so just to quickly go through the Sarkar one, and then I'll spend more time on the Kang et al. One. So this one that's gotten a good amount of attention, which is saying that I think they pushed the evidence for dark energy from 6 sigma from supernovae to 3 sigma. And there's a kind of nice paper led by David Rubin discussing what's happening. And really what you can see is on the left, this is showing 2 of the kind of measurable properties of supernovae. This is the light curve shape, which we typically called X1, or the color, which we call C. And you can see that there's trends with redshift. Now, why are there trends with redshift? So a number of this is just selection effects. So if you look like at the bottom right, you could see that for every survey, the color is getting bluer. That is a simple Malmquist bias. Basically, bluer supernovae are brighter. As you hit the detection limits of your survey, you are only be finding the bluer, brighter supernovae. Similar with X1, the higher X1 means that it's brighter, so you're finding higher X1 supernovae. Another thing you might see is in the top left, where for the nearby supernovae, the light curve shapes are more negative than for the higher redshift supernovae. Now, the reason for that is a lot of these lower redshift supernovae were found in big galaxies because the discoveries happened by surveys that were just monitoring massive galaxies. So you need to model that. You need to say, okay, well, this is a little bit different. Let me model this effect. Whereas what Sarkar says is, okay, there's just one prior on the stretch and the color for the entire redshift range. And by forcing that prior and not accounting for selection effects, you will bias your result. And if you do that, you basically can move the constraint on the evidence for dark energy from 6 sigma to 3 sigma. But that's an invalid approach because we know there's selection effects. There's no survey without selection effects. So what we do, and what I really try to advocate for is validation. And I think this is kind of the thing that's been kind of hard to catch on outside some parts of the community, So basically what we say is, all right, we're going to simulate every aspect of the surveys. And on the bottom, this is showing the DES supernova sample. And we will make sure that our simulations can predict the redshift distribution, the supernova properties distribution, the uncertainties on them, the evolutions with redshifts. And these are coming from descriptions of the survey that we know to be true. We know that there are magnitude limits of our survey, and we're putting that all in. We're putting the weather history, we're putting basically all the information we can in to then accurately represent the data. And you can see in the bottom the comparison between blue prediction and black data. And then we take this all the way to cosmology. We say, all right, we're going to input some cosmology, and we're going to see if we can recover that cosmology. So on the right, this is showing kind of going through this process, how well we recover the cosmology that we put in. And this then shows that we've validated our analysis, that we can go all the way kind of from nuts to final cosmology bolt and show that we're doing the right thing. And I feel like this is a really critical thing now, especially just as we're trying to push to this kind of 1% level. It's incredibly important if you're trying to say, hey, supernovae are completely broken in some way. But for me, kind of most of my mindset is pushing to the 1 or 2%, not the supernovae are broken, there's no dark energy kind of thing. All right, so trying to get to this Kang et al. Paper and explain what's happening here. So as you heard last week, it's kind of now known that there's evidence for a fourth standardization parameter that's related to host galaxy properties. And it's still, I'd say, unclear what this is. So basically, this is just some offset that, it's an offset as in a step, and that's kind of the more popular form, where basically you say, all right, well, I think that there's some luminosity dependence on the mass, which I'm showing 3 different plots here. And there's some cut at log host mass of 10 to the 10. And you say, okay, well, any supernovae that are on one side versus the other will get a 3% bump one way or the other. And that's in evidence from the data. And you can kind of look at the data, you can see a little something there. I think this is significant, but it's relatively small. So you say, okay, there's some step. Now let me apply it. And this can actually change your cosmology a little bit, because your relative fractions of high mass supernovae and high mass galaxies versus supernovae and low mass galaxies can change with redshift. So if, for instance, the relative fractions were 50-50 over your entire redshift range, and there was some big mass dependence or age dependence or anything, you actually would have no cosmological sensitivity to that, because your demographics aren't changing. The way that you get a cosmological sensitivity is because your relative amounts of supernovae, different types of galaxies, can change with redshift. And that's a kind of important clarification. All right, now what's still the kind of maybe the most popular one is that it's mass, but kind of what has come up, I'd say, in popularity is that somehow it's tied to progenitor age. So there's been a number of papers by Michael Rigaud, by Mike Childress or Matthew Roman that have looked at kind of different possible proxies for what could tie you to the progenitor age. And you remember that kind of all these things are leaps. They're basically saying, well, can I know how much star formation there is local to where the supernova is, and therefore I can then tie to the progenitor age. Or if I know the host galaxy age, then I know the progenitor age. But there's still a big jump in logic there, kind of going from one age to another age. But nevertheless, there's these papers that find 5 to 7 sigma evidence for this. And it's just kind of one paper comes out after another saying, well, it's mass, or it's age, or it's local star formation, or it's global star formation. And I say all these different effects are kind of within 1 sigma from each other. And one thing that has gotten missed in the Kang et al. Paper is that we're already correcting for the mass effect. So a lot of the claims in that paper are as if we didn't think there was anything. We already do. That's already kind of basic to our entire analysis. So to kind of say, oh, well, this could change things by this much. Well, we're already taking out most of that effect. This is already baked in to our analysis. So I think it's misleading to kind of start from 0 when none of the analyses start from 0 here. Okay, so what's the latest on the Kang et al. Thing? So you heard a lot about this last week, and I'll just kind of give the quick summary from my point of view. So Kang et al. Says that age is the main driver, it's progenitor age. And to do that, the group used 34 supernovae, and they cut the demographics of kind of host galaxies, the supernovae, to this smaller range. And this was only at low redshift. So they had to have a very large extrapolation of their effect. But then I was part of a group led by Ben Rose, who's actually starting at Duke next week. And the paper showed that, okay, well, if you just do a better quality cut on the light curves, since a lot of the light curves were missing pre-max data, which makes your fits pretty screwy, then the effect goes to about 1 sigma. So last week I saw in the video that Youngwook said, okay, well, I seemed to kind of could see that I didn't seem to talk much about that, but then said, okay, now he's taking this other paper led by Rose and this different sample, uses their ages and their Hubble residuals. Now it's a 4 sigma effect. So I can't speak to this as I haven't seen the analysis. And I mean, my thinking is that this will be reanalyzed, and I'm not so sure how it'll hold up. But I can say this was a plot that was put into the Rose et al. Paper. We took 250 supernovae, so this is 2.5 times this kind of new paper that is being talked about. And these are actually the supernovae that I'm using to do the cosmology. And on the right, this is the plot. So this is showing Hubble residuals from Pantheon versus the host age. And in the red line, that is the prediction from Kang et al. And in blue, you're seeing the binned Hubble residuals. And I think everyone can see that just this effect isn't there. It's not in the data. It's at least not in any data that I have used or seen, or data that's been used to do cosmology.
And
yeah.
This particular data set by Yonsei et al., we could not reproduce because the data has not been published. And you see, the data has no error bar.
Which data?
We are doing science. In science, the data without error bar is nothing. So we try to reproduce what is going on here. And what we found is that most this Yonsei et al. Data set does not match the template.
Okay.
Since the data has not been published, we try to reproduce as far as we can. And they said they used GPEG. So we consulted the developer of the GPEG, and he said the GPEG was not developed originally to measure ages. It was, as name says, it was developed for the ladder shift. Okay. So the ages derived from GPEG is extremely uncertain. And even the developer is not sure that whether he can measure ages. So without ages, we cannot tell anything. This should not have been published. This is common sense. And another one is, you said you have already corrected for the mass. And as many people suspect, mass is most likely has something to do with age, because the mass of a host galaxy cannot tell a supernova in it to be bright or faint. So it is obvious mass is not something else. And you already have corrected for the mass, so indirectly you have already corrected for the age. Now we want to see the correlation between age and Hubble residual. You already corrected for the age effect for the Hubble residual. So it is not surprising to see the scatter diagram together with extremely large uncertainty. This is very, very uncertain and should not be shown.
Youngwook, can you more or less summarize what your points are, and then we can get Dan to sort of respond to them, right? Can you give us a quick summary?
This particular diagram has no error bar.
Okay,
and
so no error bars is one, and then what else?
And the Hubble residual has been already corrected for the age effect. So we cannot see the correlation.
Okay. So let's let Dan address these points, right?
Yeah. So okay. So for the first point, in terms of no X uncertainty error bars, Sure, I'll have Dave send over data. I thought this was, I'm pretty sure this is on some website, but anyway, I'll have that sent over. That's no problem. For the second point, what you said is exactly what I'm trying to say, that we're already correcting for this. So to say, okay, this is going to totally bias our cosmology, you've said it better than I have, which is once you correct for the mass effect, you're taking out most of this age effect, and we're already correcting for the mass effect. So it's misleading to say, oh, you have this really big bias when as you said, we've corrected for this effect. So I mean, I thank you for saying this so nicely.
Let me just add one more comment. This is at given redshift. So you can probably correct significant fraction of the age effect by correcting for the mass, because host mass is a proxy for age, we believe. But as a function of redshift, the situation is very different, because the redshift range used for the supernova cosmology, within that redshift range, the mass evolution is almost negligible. Therefore, even though you corrected for the mass, this will not introduce any systematic bias in cosmology. However, if we had properly corrected for the age, as you know, age is a strong function of redshift. So we have a strong systematic bias. So, I mean, frankly speaking, the correction with mass is most strange correction that I ever seen in my life during the last
actually, Jungkook, I think most physicists
can
would
be
agree with you on
but
this.
Post mass.
So,
okay.
Well, some functions are very bizarre.
I'm gonna get to my theory of what's going on, but so let me try to address this next thing. So there's a nice table which is showing. Okay, here's the Rigaud et al., which is kind of similar to this age effect, and the prediction is that you can see on the right, this would be 0.34 mag fainter, and then this paper 0.27 mag fainter. So pretty similar. Now in the Rigaud et al. 2018 paper, they predict the cosmological. They bias on distance modulus, and that's what you can see on the bottom left. So they try to do this thing where they say, okay, well, we have this big effect, and I frankly think that even that effect is much bigger than what's in the data. But then they put that in, and they find the change in distance modulus from z equals 0 to z equals 1 goes from minus 0.08 to minus 0.03 or so. Now, when you do this, you get a bias from z equals 0 to z equals 1 of 0.25 mag. So about a factor of 5 times bigger of a bias in the cosmological distance modulus for essentially talking about the same effect. So this is a huge difference in what the impact has been on cosmology. Mikkel Rigaud et al. Is saying 0.05 mag, you're saying 0.25 mag. That's the difference between saying there is no dark energy versus this is a systematic. Now, I want to add one other thing, which is, as shown in Rigaud et al., if this is true, what you expect is that the mass step should be getting smaller with redshift. Now, actually, in Pantheon, we saw something not far away. I'm sorry I didn't include this, but not far away from what Rigaud et al. Would predict. And so I said, okay, well, in my nominal analysis, I'm going to assume there's a single mass step that's not changing redshift. But as a systematic and Pantheon, I allowed, and it changed W by 1%. I mean, you have to do the whole thing together. You can't just say, well, here's some effect, I'm going to extrapolate it based on some big sample. You have to do it as part of your whole analysis. Taking one thing in isolation and extrapolating it will cause to bias results. And I did this kind of consistent with Rigaud et al., and it's a 1% change in W. It's not getting rid of dark energy. So I'm happy just to let this story unfold. We could keep going back and forth, but there's things here that just don't make sense to me.
Yeah, I have a lot to say, but I will wait.
Okay, sure. Okay. Anyway, I'm here all night. Okay, so there's still this question, and I want to get to what I think is going on. So I put out this paper with Dylan Brout offering a totally different explanation, and I will say I do not have the certainty of what's going on that Youngberg seems to have, but I think we're getting closer to the truth. All right, so there's three key mysteries that kind of have been difficult for the 1A community in the last decade. So there's this question that I've now talked about: why does it appear that Hubble residuals correlate with properties of the host galaxies of type 1A supernovae? Then there's this 10% amount of intrinsic scatter of Hubble residuals, and this is kind of after standardization. So what is this due to? And then there's been this question of how does the supernova color relate to the supernova luminosity? And we've kind of always been doing this simplistic thing about supernova color, but we know that this should be more complex. So let me try to dive in there. All right, so when I talk about intrinsic scatter, what I mean is that beyond measurement uncertainty, to get the Hubble residuals in the bottom to give you a chi-squared of unity, reduced chi-square of 1, you have to add in some error floor, essentially, so what we call the amount of unexplained scatter, if you will, on the level of about 0.1 mag. And it's been this question of, well, what's driving that 0.1 mag? What is it? Is it some kind of just totally gray achromatic offset? There's some color dependence? So there's these different scatter models that try to explain this. So we have this question. All right, then there's this question of, well, what's going on with supernova colors? And we know that even in the Milky Way, there's not a single R sub V reddening law ratio that in the Milky Way itself, R sub V is varying. Yet what we do in our supernova analyses is we basically fix a single correlation between supernova color and luminosity for all the supernovae. So that is kind of, I think any astronomer would say that is not a wise approach, but it's simple and it's doable, and that's what we've been doing. And when studies have tried to measure R sub V directly from supernova spectra, they see a wide range. So we're basically fixing a single one, but any study that has looked at this has seen a wide range. But in our kind of big standardization papers, we assume a single one. Then I say that we've also kind of in the past, so this was really popular 20 years ago with a fitter called MLCS. There's this understanding that when you measure supernova color, that part of the supernova color is intrinsic and part of it is dust, right? We know that there's dust around these supernovae, but the community has kind of moved away from that, saying basically all colors are the same. It doesn't matter what's intrinsic, what's dust. They all have the same color luminosity relation. They're all kind of consistent, and that's a simplistic point of view. And we know that Milky Way shows that this is absolutely wrong. Now, what we show on the right, so this is using like a Pantheon plus sample. This is a histogram of the color, and what you could see on the top right there is that there's kind of this extended rightward tail that looks like a added dust distribution. And then what we see in the middle panel is that if you look at just the standardizability scatter of type 1A supernovae, it goes up with color. So basically, redder supernovae are much less standardizable than bluer supernovae. And then if you look at the Hubble residuals, this is the bottom panel, and you plot that versus color, that there's this really strange trend. Now, if this whole story was just something to do with progenitors, you wouldn't see kind of all these different effects. You shouldn't see some really strong dependence on the color. And I'll try to hit the nail on this in just a second. So what we tried to do is return to basically the kind of older dust-based model, but kind of do it in this newer framework where we use the kind of newer fitter and kind of the spectral model that people use these days. And basically say there's two components. There's some intrinsic component, which we call the parent color, and that you're seeing in the left column. And that's just some Gaussian. And then there's some dust model, and that is asymmetric. Dust can only make things redder. And if you combine the two of those, that they can then reproduce these three kind of very strange trends that are in the data. And this is data with 1,400 supernovae. So this is kind of much bigger than any of the samples I've been talking about before. So these are kind of three very unique signatures. And the way that they can be understood is that supernova colors have an intrinsic part and an extrinsic dust part. And the reason that the scatter, what you kind of see in the middle panel, the middle, that the scatter is going up for supernovae with redder colors because there is a spread in extinction ratios. So basically, we know from the Milky Way that there should be this spread. This will cause the scatter for redder supernovae to have to be much bigger than for bluer scatter. This will just kind of come out naturally from your model, or else there's really no way to understand why is it that red supernovae look so much less standardizable than blue supernovae. Now, I'll just say, going back a point, that these trends that I'm pointing out here, this is an 11 sigma effect and an 8 sigma effect. So these are not kind of small little things that will go back and forth. These are kind of absolutely deep in our data. Okay, now the kicker of this is if you break the supernovae up into kind of supernovae and low mass galaxies versus high mass galaxies, which I talked about before. And what you can see is actually the scatter has a strong color dependence, and it is much higher for just the red the red supernovae in the lower mass galaxies. And kind of what's really neat looking at the bottom panel is if you plot this mass step versus color, what you could see is that for supernovae that are blue, there's no mass step. But as supernovae get redder, it linearly depends on color. So how is it the mass step itself has such a strong color dependence? Well, the way that you can predict this, and I think the only way, is saying that actually what's driving this mass step, this kind of big confusion that's lasted for so long, is that different types of galaxies, either local or global, we don't know, have different reddening laws. And that is something that is absolutely predicted by any astronomy dust model, that the different types of galaxies have different extinction ratios. If you'd say that they should all be the same, we would be laughed at. Now, what you could do if you kind of put in these models of these distributions of extinction ratios, what I'm showing on the right here I'm showing the Hubble residuals versus color for supernovae in high and low mass, and you could totally predict the trends seen in the data. So if this was progenitors, then there's no reason that the progenitors should have some dependence on the supernova color, so that the step so that like a red supernovae will just go off when the progenitor is this. I don't know what the story is, but there's a very simple story here of that we know different galaxies or the environments around different supernovae should have different reddening laws. And if you just put that in, you could explain these 11 and 8 sigma effects in the data. So this is kind of what I think is going on. And this has already kind of gotten a lot of attention. I'll talk about that just in a second. But to me, it hits the three mysteries. We're not pushing in new mysteries at this point. We're just saying, hey, we've had these three problems. It turns out there's one solution that could explain all these three things. So I think this is really powerful. I think it deserves a big look. And I'll also just say that even basically rethinking kind of the entire dust model, trying to explain the mass step in a totally different way, if you actually do this the whole way through, this causes a 4% bias in W. So to my point earlier, you can't just kind of go from, oh, I see this big effect, to there's no more dark energy. You have to put this all the way in. And this is, I think, a much more drastic interpretation, different interpretation from what we've been doing. But if you kind of put it all the way through, you refit, you re-standardize, you re-look for nuisance parameters, you only get a 4% bias. So to me, that's actually quite huge, 4% is. But this isn't a 100% bias in W. This isn't removing the need for dark energy, and you have to do this whole thing together. Okay, so then this paper came out, I don't know, at the beginning of COVID, and since then there are these two papers that are using a lot of the same data. We said, okay, well, if this is true, that this is really just dust, then the step should change depending on what band you're looking at it with. So if you're looking in the optical versus you're looking in the near infrared, well, in the near infrared, we know you're less sensitive to dust. So then we expect the step to be smaller, which I agree with. Now, these papers came out saying, okay, well, we see a very similar effect in the optical and the near infrared. So this is showing one from Ponder et al. And I think that they'll be changing their interpretation soon, because there's a lot of discussion about this. This is the kind of key plot from the paper. And here they're showing the evidence for the step. And on the bottom, this is the Hubble residuals. On the top, this is basically the significance of their thing. And what your eye should see on the top is that there's just a really strong, sharp peak at a very specific step of about 10.4 or so. Now, for anyone looking closely at this, you say, well, why is this happening? If you just look at kind of all the points, there's nothing by eye where you're seeing any strong evidence for anything. But what's happening is that they're taking the uncertainties that come straight out of the fitter, which are just the measurement uncertainties. So if you look at, let's say, the lowest point on the bottom left at 10.5, that is something like a 50 sigma outlier. And that itself is pulling this whole step. Now, if you do outlier cuts, or you basically add in the intrinsic scatter, as I talked about before, this step goes to 0. So in no way would I say this has shown that kind of the dust explanation I've worked on is incorrect. I think this is the right thing to look at, but this by itself is clearly just getting pulled by outliers. So is not it. So I'm working on a near infrared program basically to do something similar. And I think this is a really exciting approach, but you have to do correct error propagation to say kind of whether this effect is there or not. Just these uncertainties are way too small, and it's a really key point that you have to add in uncertainties so you don't have 50 sigma outliers. Okay, so I say to be determined about this. I'm definitely looking forward to it. It's clearly kind of this idea has gotten a lot of attention, and we'll hopefully learn more about this soon. Okay, now I kind of want to say as a general note that, so I put out Pantheon. I mean, the first time it's not perfect. There's now been a number of things that kind of I think that I want to do better. So this is kind of nice plot from Colgáin 2019. So showing this is something that didn't occur to me. This is changing the maximum redshift and looking at omega matter and showing that there's kind of this funny structure to it that it's kind of unclear what it's due to. And I mean, some of these things are systematic. Some of the things are kind of weird statistical fluctuations. I can't say I understand all of it yet, but I do think it's important to just kind of remember the broader context, which is that we have multiple probes all saying the same thing. This is not kind of Pantheon alone. This is not supernovae alone. There's a kind of very clear picture of omega matter 0.3, omega lambda 0.7. This is kind of concordance cosmology, as they say, and it's very hard to just kind of say, okay, well, actually Supernova wrong, and they predict omega lambda of 0. I don't see how this either fits in the data or fits in the story, this kind of broader story using other data sets. Okay, so that's the end of my dark energy section. I have an H0 section, but we were 10 minutes till the hour, so maybe should I stop here and just open up for more questions?
Dan, how long is your H0 section? It would be 20 minutes, 30 minutes?
20 minutes, I think.
20 minutes, okay. And you can't summarize it, or?
Yeah, I'll do a quick.
Let me ask you, first of all, let's ask if there's any questions here. Does people just want to discuss dark energy? If there's no questions, then do you think you could summarize it, or?
Yeah, well, let me just give a couple highlights.
Okay.
Oh yeah, go ahead. Yeah,
just summarize. Yeah, just cut through it, right?
So I'm part of the Shoes team. Basically, we use essentially something similar to the Pantheon sample. Well, that's what we used in 2016. So everyone knows that there's this tension now. So this is Shoes work's led by Adam Reese. I think might give a talk for you guys at some point in the near future. And I want to say that basically that the measuring H naught, what I have to do on the supernova side is essentially compare supernovae at Z from 0 to 0.01, so very nearby supernovae in galaxies that also host Cepheids, to supernovae at about 0.05. They're kind of in the local Hubble flow. So this is kind of comparing similar supernovae. For W, it's much harder. Basically, the leverage comes from comparing supernovae Z equals low Z, 0.05, to Z equals 0.5, where you have different surveys, K corrections, filters, you have to worry about evolution as we talked about. So in some sense, W is a much harder measurement on the supernova side than H naught. And maybe present company excluded, there's kind of a lot of people that would trust supernovae for W, but not supernovae for H naught. And to me, that's a bit backwards, that because one is just kind of a much more difficult and sensitive thing than the other. Now, let's quickly say just two things. So one, it's come out in a number of papers that maybe we're living in some void. Well, we can use supernovae, basically can trace out on the early and kind of inside the void and outside the void, and we can look for a kink. And kind of in the blue line, that's a prediction, a kind of popular void model prediction. And then black, that's the data point. And basically, we just don't see any evidence for a kink kind of from n-body simulations, just a prediction that something would be this big. And kind of in red, that's basically Planck. So we're nowhere kind of close to Planck when it comes to void models. And I'll say one other thing, just this ties back to all this mass, the mass step conversation, which is that the measurement of H naught actually has a built-in protection. So this is kind of showing the distance ladder, and basically we use supernovae in the second and third rung of the distance ladder. Now, as long as, let's say I mess up supernova in some way by 100%, as long as I mess up supernovae the same way in the second and third rung of the distance ladder, this would have no effect on H naught. It basically cancels out because the same thing that's happening to the supernova in the second rung are happening to supernova in the third rung. So there's this protection in the ladder itself. And the systematics that we're worried about are anything that could be affecting supernova in your second rung differently from supernova in your third rung. So one of those kinds of things could be, well, maybe the host galaxies are different in your calibrator, the calibrator set, your second rung compared to your third rung. And this has kind of been an exciting thing of possibly explain part of the H naught tension. Now, to actually do this out, you have to basically multiply the size of the step by the demographics difference of the kinds of host galaxies in the calibrator set and the Hubble flow set. And if you had a 0.06 mag step and a percentage difference of 0.25, that's about a 0.8% difference in H naught. So it's not that big. But what we now do is we say, all right, well, let's make sure our host galaxies are as similar in the calibrator set as they are to the Hubble flow set. And if you just look at kind of the last column, you can see that the change in H naught is on the level of 0.3 or so. So if the tension with Planck is 7 in H naught units, this is just a really small fraction. And we've really kind of done, I think, a good job in making sure that our sample in the second rung and third rung are as similar, so that the bias in H naught is 0.1 or so. It's just this is just not what's going to explain the tension. Okay, and then lastly, I'll just say about supernovae that the Pantheon supernovae are now used with baryon acoustic oscillations in an inverse distance ladder, and they give a low H naught, or with the same Pantheon supernovae used with strong lens systems, and they give a high H naught. So Pantheon kind of acts like the middle person here, and you'd have to concoct a really crazy thing about supernovae to kind of explain all this. And it basically, to say that supernovae, that they show there's no dark energy or something, you're really kind of showing a significant inconsistency with multiple other probes at the same time. So while I've said you could get rid of supernovae and then all other probes are fine, but if you do want to say supernovae are wrong, you're then making supernovae inconsistent with these other probes. So I will end with that, and I'll just kind of leave with just H naught plot of kind of all the consensus from on the local side. Just take any more questions.
Okay, Dan, thanks very much for the talk. So I guess we're open for questions or comments. Anybody has one?
Well, I have one comment, of course.
Yep.
I'd like to emphasize this. Getting scatter diagram in science is very easy. Use very uncertain data. The more such data, the better. Better yet, data without error bar is even better, where the error bar can be as large as the age of the universe.
Yeah.
We should not do that. We should not show the data without error bar in independent variable. So don't use the Jones-Edel data anymore. And getting correlation, however, is very difficult because everything must be correct in order to see the correlation.
Okay.
And now even the data set originally used by Rose and Risedol to oppose our claim is now strongly supporting our conclusion, even more so than our original correlation. So this will be soon published. So, and I will send you the paper, but you can already see that in my slide.
Sure. Look, I think, as I've talked about, there is some effect. I've seen plenty of people see some age effect. I think, in the sample that you released, there were some issues there, but I still think that there's an effect. I mean, I've written a lot about this. My point is, as I think you've said nicely, we're correcting for this effect. We include this as a systematic. We're doing kind of everything we can, and this just isn't moving the needle that much. So I'm not sure what else we can do besides put in this effect as a key systematic with and treat it like every other systematic. I'm all ears. My goal is to put in as many systematics as I can to try to break as many things as I can to give the best measurement possible. I have no other agenda than that. So right now I'm working with Rigaud's group to try to model things and put this in even kind of more realistic. But I still think you have to do this all together in your analysis. You can't go from, I've seen this in this one sample and this some effect to, oh, now all of 1A cosmology is broken. That's just such a huge extrapolation. And
we are just talking about supernova cosmology. I would love
to work with you. I'd love to work with you to do that better. I generally say that.
Yeah, we are just talking about supernova cosmology here. We never said PAO or CMB.
That's something else. I think the burden should be on showing that kind of what you're doing can be validated and is consistent with everything else that you're doing in your supernova cosmology analysis. I would love to do that with you.
Any more questions or comments?
Hi, I have two questions, if possible. Yep. Stephen, thanks for the talk. It's very good. So the first is the next generation of supernova catalogs, you're going to have many more. What kind of gains do you expect to see? Is there going to be a systematics flaw, or you just keep getting better constraints?
Great question. So LSST will start, now the date is 2023, early 2023, and then WFIRST is saying kind of mid 2026. LSST, so the Pantheon sample has a little over 1,000 supernovae. I think kind of the next DS analysis will add another 1,500 supernovae. So I think kind of in this generation, or stage 3 we call it, there'll be maybe 3,000 type 1 supernovae. Then with LSST, we're going from 3,000 to something like 400,000. So we're getting a good factor of 100 or 2 orders of magnitude. And then WFIRST, where it'll probably be about 20,000 supernovae, but it'll go much deeper to much higher redshift. So any of these kind of evolution questions with WFIRST will be answered pretty easily just because we'll go to such higher redshift. Now, in terms of systematics, that's a really tough one. The optimistic part of me says that if you look at the error budget from any of the last big 1A cosmology papers, the statistical uncertainty and the systematic uncertainty have been very similar. And it's not a coincidence. It's just that I think people see where the systematics are, or sorry, they see where the statistical precision is, and they keep pushing at their systematics so that they're not dominated by systematics. And also, kind of as you have more statistics, you actually can learn something about your systematics. Now, so my hope is that that will continue with LSST, but there's some things like calibration, for instance, that that it doesn't just get better with more statistics. So it's unclear if we're just going to hit some floor hard. I hope not. I see a good enough room to keep working on this for the next handful of years, but I don't know. That floor could just hit us in the face really hard at some point.
Okay, thanks. I do have another question, if possible, quick one. So there's some people who'd say the very low redshift, but we actually don't know what the correct metric should be to describe photon GD6. So they simply cut below the homogeneity scale. They say we don't have a good theoretical model for the light propagation. So if you removed all supernova from, let's say, redshift below 0.05,
yep.
What would that do to the cosmology?
Yeah, I have this great question. This number in Pantheon, it blows up the, it increases the uncertainty. I think the uncertainty was 0.04 or 4%, and it goes to, I think, 0.055, and then W doesn't move that much. Part of the reason is that the low redshift sample is old, and it has a kind of number of systematics of things that I'm a little unsure about. One thing is like this mass step. So in some sense, I've already kind of de-weighted the Z less than 0.05 sample with systematics. So if you just take it out, the hit is just isn't so bad.
Okay, that's great. Thank you.
It looks like Armin has a question. Armin, something?
Dan, this is Arman. Just one question: that are you working on any new compilation? Particularly, should we hope for some high redshift supernova? I mean, particularly higher than 1. I mean, in the near future, next 1 or 2 years.
So I'm working on a new supernova. I'm basically working on Pantheon 2, and I'm somewhat hopeful about that. And so basically, Shoes will have its next big H0 paper out in, let's say, 4 months, something like that. And my hope is that there's another Pantheon paper to go with it, so you could do all the covariance together. There'll be new DES data, but that's less than Z of 1. Then kind of other people, this kind of a lot out of Japan, like now Suzuki is working on the Sushi program, and this will have a decent number of Z greater than 1 supernovae. I think their time scale is like a year away from what I hear. It's I think mean redshift like Z of 1.25 or something like that. The difficulty they have is a lot of the supernovae are photometrically classified. So you're not totally sure they're type 1a supernovae. And so they have to work through that. But that's what I would look forward to on the high Z end.
Thank you.
Yep.
Okay, that may be the last question then. Okay, so if there's no more questions or comments, I would like to thank Dan for a very interesting talk.
Great. Thank you everyone for all your time.
Okay, all the best. Take care.